Start Recording. Ist mir nämlich schon ein paar Mal passiert, dass ich was aufgenommen habe und dann war nur der Bildschirm drauf, aber nicht mit, was ich erzähle. Das ist dann natürlich nur semi-gut. Aber das funktioniert jetzt. Gut, dann machen wir mal mit unserem int-Projekt weiter. So at the end, last week we have that's the wrong project. Worked on our int, and the last thing we did was implementing the very simple bitwise operations like AND, OR, and XOR. And we had some homework, which should be easy enough to do. We have implemented a to-bin and from-bin, which is quite nice and useful. And today we will continue with the operators, so with the different operations that we can do. We can mark here the things that are to be done, so that we know what is and what isn't. To do and to do, and I think invert was also a to do. The rest works, and one thing that we are still missing, as you might have noticed, is the ability to compare numbers. Obviously, comparing numbers is something mighty useful, something that usually you would want to be able to do with numbers. So we will implement such a compare mechanism, and we will, like with the other operators, first make a function that does the actual job and then implement the operators using this function. And the trick here is that we'll have a function called compare, which just takes another big int as argument, and it will return an integer. The const function, it doesn't change anything, and the way it works is 0 on match, 1 when other is the, or -1 when is lower. And such a function allows us, this is 0, it looks like an O, no, it's a 0, and such a function allows us to implement all the 6 typically useful comparison operators using just this one function and comparing its output to one of the different values. So bool operator less than other const is simply return compare other less than 0. So as you see, it's quite convenient, and of course greater than. Here we just make a greater 0. For is equals, we just make is equals 0, and then the other few less or equal, greater or equal just gets changed to greater or equal 0, and and the last one unequal is not 0. So we have gained quite a lot of functionality with only a single function that is being used in a smart way. So we will of course now want to implement this function. Let's find a good place for it here, for example. And we would need a volunteer, someone who would like to try to implement it. It is not difficult. It can be done chunk-wise, so there is no carryover yet or anything complicated like this. It's quite straightforward. The approach would be just to create a loop, for example, like in the XOR, and then just compare the chunks in the right order, one to the other and to the other, and as soon as we encounter one chunk which is different, then we return the right value. So we would go from the most significant chunk, and then based on that just run our loop and do the comparison. So shall I designate a volunteer, or is there someone who would like to implement it? So maybe Mr. Thala, would you like trying to implement it? Hello, hello, are you there? Sure. Okay, so well, the best learning is when someone tells you what to do, but if you want the next time, then the next time is fine. Okay, we had already Mr. Kaufman, so it wouldn't be fair to get him again. Then Miss Chiara. Then you just need to connect via VNC so that you can take charge of the virtual machine we are seeing. Um, let me check it. Probably, but I'd rather check. The, so I put the IP in the chat, and you need the port number, which was after the double point in the last assignment. I think just need to check the selected port. That was 699. So it will be, that should be the full address. If this is correct, let's see. Yeah, that should be fine. It should not ask for a username. It should only ask for a password. If it's asking for a username, then you didn't add the 6990 after the colon. Just try again. Here it is not connecting. That is not good. If this doesn't work, let me try quickly from a different device. This goes off. This stays on. VNC, new device. When I try it, it works correctly. Try again and make sure that you add this 6900 to the end. Ah, now it works. Alright, this you can close. Mm-hmm. Mm-hmm. The easiest is to just take a look how we implemented, for example, the AND or, because there were a few things before the loop that we had to do. Exactly, that we have to check the sizes. Well, one will be 1, the other one will be 2. Let's think about it. So we start with the first chunk in the block, but we want to start the comparison from the most significant bit. So we should start from the last chunk. So we should start from the back. So the loop in the previous example, it starts at the front. Oh, and I see we have actually a small bug in the old code. We'll fix that later. But first we need to get the two sizes, count 1 and count 2. And then we can start the loop. Hmm? Well, you need also the if for the case where the size is not a multiple of chunks, so that we add one more, so that we have definitely the right value and are not omitting some bytes at the beginning, at the highest order bytes. Here I think you put an underscore instead of a dash at the arrow. That's why it's red. Yeah. Mm-hmm. And now we can start our loop. Just that we want to run it, I think, at least I think we want to run it in reverse. Well, there are two strategies how we can run the loop in reverse. Either we, as said here, just start with I0 and go until I less than max, you count 1 or you count 2. And then inside the loop, wherever we use E, we subtract max you count from max you count 1, you count 2, the I value. Or we just start the loop here directly going the other way. So instead of I is equals 0, we would start with I is equals max you count 1 or you count 2 minus 1. And then we would use in the increment function the I minus minus to decrement. I minus minus, we want to go the other way around. And we also want to, there is something missing, right? So first of all, what the I is equals max you want to have in the initial part. So remove I is equals 0 semicolon at the beginning. No, here you can leave it, this part for now. Let's first start the beginning. Just remove the I is equals 0 semicolon so that you have int I is equals max. And then between this and the I, you need a new condition, and the condition is I is greater 0. Greater or equals 0 to be exact. And here there's also, so this you can go to the other semicolon which we have in the line, add a second semicolon, and between the semicolons write I is greater equals 0. And we need one more thing. After max, after the closing bracket, we need to add minus 1. Because the count is already an index once too far. This way, as it is written now, the loop will start at the highest order byte, or rather highest order chunk, and then go downwards to the least significant chunk, and it will and I will always be a valid index for our chunks. So now inside, what we want is to get a copy of both chunks, the same way we did in the AND or function before. So in a safe way that it will give us either the value from the pdata array or just give us 0 if we already exceeded the array in case the two numbers were not the same size. And then we just have to compare those two chunks to each other. Mm-hmm. Correct. Well, I not 1. So good so far. So far so good. The u is should be lowercase. That's why it's complaining. There are other languages which are not case sensitive, which might sound convenient, but really it's just an invitation to make mistakes. Somehow two characters are missing. You only have the closing bracket, but the opening bracket and the I somehow were dropped in transmission. Okay. Great. Now we just need to compare them and return 1 or -1, depending on what we encounter. We don't have a result variable here. We just directly return an integer value. Basically, we'll have two ifs, which compare first if one chunk is smaller than the other, and then if the other is smaller than the one. And if any of those cases is true, we return instantly, returning either 1 or -1, depending on which one is greater. And which one and how we want this to behave, we have written in the header file in which scenario we want to return 1 and when -1. And from inside the loop, we always only return 1 or -1 on a mismatch. And after the loop, we'll return 0, indicating that we went through the whole number and everything was the same. Correct. You don't need to use the compare function. You can just really use the greater. Sorry, not you count 1. You just have to compare chunk 1 and chunk 2. Just smaller. Well, it should be an if, so if this, and in the next line then what it should do if the if evaluates to true. And if wants brackets. It's not MATLAB script. I know in MATLAB script you just write if and then the condition, but C++ always wants the condition to be in normal brackets, round brackets for the condition. Curly brackets you only use for code blocks. We need a closing bracket after the number 2. Yeah, and putting everything in one line would make it look nicer. And the thing about ifs and fors and everything is you only need a code block with curly brackets if you have more than one line of what you want to do conditionally. If you just have want to do one operation like return, you don't need to put it in curly brackets like we did with the count 1 and count 2 plus plus. It can be written directly beneath. So now you need to return. The question is just 1 or -1, and which one of those we have written in the header when we described how the function should behave. So we can switch to the big int h to find out what should happen when. Yes. Well, we just said the opposite, didn't we? If the other is greater, when other is greater, other is chunk 2. Wait, let me see, maybe I'm right. Click. Ah, yeah, you're right, sorry. And then just the other case for -1. It's not an... Well, you can make an else case, sure. But that would be else if. just if is good enough, because since you have a return statement, you wouldn't reach the else branch either way. Right? Here we don't have any more cases. We don't want the equals case, because if it's equals, we want to proceed to the next chunk. So we just go once after the loop. So when the loop stops looping, so to say. And then there we just give a return 0, because if we arrived at the end of the loop without returning 1 or -1, it implicitly means that all the chunks were equal. We just need to add the line between 190 and 191, which says return 0. Okay, good. Then it's ready to be tested. When you go to the main function, you could set up a new test case, like call it, I don't know, test CMP. Well, so you make a function above the main function called test CMP, and then you have to call it from the main function, of course. Here you are already inside another test. You need to put it, so remove the 4 letters, and in line 122 you can start a new function. The test function does not, well, you need to first maybe just take a look how these other test functions are implemented. So as you see, we start first with a boolean, so the return value of the function, and we say the name of the function, then normal round brackets. Yeah. Then just round brackets, since we don't have any arguments for the function. And then with curly brackets, starting at the next line, you start a code block, which will be the function itself. Ideally, just create both brackets. Visual Studio out of the box is configured such that it always makes you closing brackets, but I always turn it off, so here in the VM you need to do it manually. And then you basically just need to define a few, well, 2 numbers, which we will be then comparing and testing whether they are doing what we want them to do. Well, const big int probably, and const you start with a small letter, not capitalized. So instead of char, write c big int, and instead of the equal sign, you can open a round bracket and enter a value that you want it to have, as long as the value is 64-bit or less. So I think since our chunk size is short right now, then this should work quite fine. If you just enter a large enough 64-bit number as a int64. You don't need to write int64, you can just start typing 0x and then in hexadecimal notation the value. A 64-bit number has 16 nibbles, so 16 letters A to Z. And just a small anecdote, a byte, I guess everyone knows what it is, 8-bit, but a nibble is 4-bit. And in hex notation, each position of the number represents one nibble, which is quite convenient. Decimal numbers unfortunately don't map in any nice way to binary, so while they are nice for humans, they are a bit annoying to work with when programming and so on. Yeah, and then 10 zeros, for example. That's not quite 10 zeros. That you need more zeros. Yeah, and then you make another number 2, which we change. You need the semicolon. In principle, it can be the same number, but starting with not AB but BB or something like that. Now here you need to here just close the bracket and put a semicolon after it. And then in the new line you make another big int called number 2. Just something where we will be able to tell whether it's bigger or smaller by looking on it without having to use the calculator. But here we already see that it will be greater because it starts the highest order nibble is greater, so the number will be greater no matter what the rest is. So you can fill in the rest just with zeros or with whatever you want. Yeah. I think there is 1 0 too short. Okay, and now you can just write test cases like on the in the above function, basically just comparing in ifs the two numbers using the different operators, and then comparing the result with what you say it should be. So for a simple test, you could write open brackets again, round ones, and number 1 equals number 2. Close brackets. And this must be, so if it passes, so if it's correct, then the result of this should be false. So if this is unequals false, unequals means exclamation mark equals false. Close brackets. And now you open a code block and just write printf begin compare failed, and in the next line return false. Yeah, you also need a semicolon in line 129. And then you need a closing bracket after the false. Yeah. And now you just repeat this for the other operations that we would want, and do the other tests. So is it greater, is it smaller, and so on. Yeah, and you can copy this. That makes it easier. You can also use the shortcut Control C. It didn't work. When the menu is open, the shortcut doesn't work anymore. You have to use the shortcut before you open the menu. Mm-hmm. Yeah, number 1 is smaller than number 2, so in line 134 it should return true. So if it's unequals true, then it failed. No, return false is always return false. You need to change the expected value of the comparison. The comparison is 1 less than 2. So is number 1 less than number 2, which it is, should return true. So if it doesn't, it's a failure. Yeah. And for the other one, it should be false. False is correct. And I guess that's enough test cases. And return write a success message and return true. I think it would be boring to just copy those lines 6 more times and to the individual other operators. If this works, then it works. Okay. Good. Then go to the main function. Down. The main function is at the bottom, and just add a call to test compare. Yeah, here's the next one. Okay, semicolon, and let's run it. The window opened on the very right here. Says the second comparison failed. Interesting. Let me have the mouse. Let's see. So it says that this here failed. Why would this fail? So 1 is A is less than B. That should be correct. So let's see. Let's put a breakpoint here. Let's run it. We'll get inside. So here we can test if this is less than 0. And here now, when we are comparing, so first chunk AB, BB, and it returns 1. And 1 is not less than 0. This means that okay, wait. So let's see if we have the right condition. So we said we want 1 if other is greater. Other is, in this case, number 2, and 2 is greater. Okay. Then it means that here we have screwed this up, so this is easy to fix. Just switch those around and now it should be fine. Let's run it and test passed. Very good. So this works. So this is so far completed. Just one small detail: if we redo the closing bracket, it will format the code and fix the indentations. Also, we should add a line here, but this is just for readability. That has no functional difference. Good. So we are done with this. So let's see what else we can do. So we have binary operation, we have comparison operations, we have assignment operations. So the next thing what we will want to do will be some arithmetical operations, obviously, like add and subtract and divide and multiply and so on. So we just copy some reference thingy to modify, and 1, 2, 3, 5. So we have plus, we have minus, we have multiply, divide, and we have modulo, so the remainder. And then we just copy this again and change it accordingly to make the assignment style operators out of it. Of course, then it's no longer const. Then we will of course need the operations, add, subtract, multiply, divide, and modulo. Zack. Add, subtract, multiply, divide, and modulo. And here it's slightly different. I can copy the line from here. Add, subtract, multiply, divide, modulo. Oops. Cute. Yes, you can disconnect. Here would be a good place for it. That might be enough. Subtract, multiply, divide, modulo. And the multiply, divide, and modulo, that will be the next homework. And the add and subtract we'll try to do today. Let's see. Homework 3a from the 16th. Implement this function. Yeah, that it multiplies. That's self-explanatory. B and C. Or 3C. So when you search, when you research for how to implement division, especially in some reasonably efficient way, then you will run across implementations, algorithms which usually are a function that which take the two operands and has to return values, the result of the integer division as well as the remainder that remained. And then it is expedient to just add such a helper function and then just call it from divide and from modulo, and then just pick which value of the two return values you want to return from the actual function. And for multiplication, there are also good algorithms that do that reasonably efficiently. The preschooler approach of just running a loop and adding the same value over and over and over again is of course highly inefficient, so that is not a valid solution. It should be something reasonably fast. And now let's take a look on this add and subtract functions, how we can make them during the lecture. First of all, is there someone who would maybe like to try implementing those? No one? Interesting, someone just disconnected when I asked. Let's see who that was. The same smart student who did this the last time I asked about a volunteer. Sneaky, sneaky. That person will be volunteering next time involuntarily. Right, so any of you who would like to try? If not, let's see who wasn't yet maybe Mr. Ali Azim. Would you like to try? Would you like to try? Hello? I heard something and then I... Hello? Hello, hello. Well, that doesn't seem to be working. Then maybe Mr. Ali Usman. Would you like to try implementing one of the two functions, the add or the subtract, for our big integer? So just to outline how we would want to do it, we would start again with the same code block like we did here. So this part would remain the same. We can even copy it here, but we will need to make the insides of the loop significantly differently. So this operation is no longer byte-wise. So as when we take a look again to these operations, they were quite trivial because we just took chunk 1, in this case XOR or AND chunk 2, and then we just assigned this to the new chunk, and that was it. With addition and subtraction, it's a bit more difficult because when we add values to each other and the two values in sum are larger than what can be contained in one chunk, then we have a carryover, and we need to implement this carryover mechanisms so that we don't lose values while doing the addition. Right, so we had this skeleton already, and you can think about how to implement the that mechanism. Well, in principle, we just need to first do the addition. So um, since we are starting here at the least significant chunk, the loop already runs the right way. So a good start would be to just write result mptr arrow p data from I, and then is equals chunk 1 plus chunk 2. So really just do the addition, and we will be thinking of about the carryover in the next line. Can you connect, or is that not working? Mm-hmm. You need the VNC viewer, which you can download from realvnc.com for free. And then you enter the address which is in the chat. I can post it again in case you came in late and the chat is not shown. So that's the address. In the Zoom chat, there is a IP address and a port number, which you have to enter into the VNC client to connect. Is it working? Is it asking for a password? That is quite easy. So you have real VNC viewer installed? Yes? No? So can you open it? The real VNC viewer can be downloaded from real VNC. I will post the link in the chat again. Real VNC viewer, that sounds like the right link. Zack. So just download the version for your operating system, I guess Windows. And then once you install it, there will be one window asking if you want to share data and to log in. You just select you don't want to share data, and there is a text continue without login. And once you did this, you will get this window. And here in the address line, you just have to enter the IP address with the port that has been posted in the chat as well. And a small hint to all the other students, please install VNC Viewer so that you are ready to use it once it's your turn to do something. Yes, maybe that's a better idea. Mm-hmm. Yeah, that would be a good start. No, to add them you just make plus. Sorry, you just want chunk, you don't need MPTR data, you just write chunk 1 plus chunk 2. But the result is not a chunk, result is, you need to write result MPTR, so result arrow MPTR punct pdata from I is equals chunk 1 plus chunk 2. Should be, why is it complaining? There must be a small typo somewhere. Sorry, punct dot not arrow. It's not a pointer. I think if you click somewhere else. Yeah, and pointer and then arrow. That PTR arrow pdata. Now it's fine. Okay, so we just added them, but we might have caused an overflow, meaning the value inside pdata I might actually now be lower than either of the two chunks, because we had the one which we shifted out of the value range, and then if you are missing a 1, then the thing will be smaller, obviously. So you need to check if this happened. If this result value is less than chunk 1, well, not just result, the whole thing of result dot mptr data, and so on and so on. And one might think, is it needed to check for both cases, chunk 1 and chunk 2? But as far as the theory goes, it really is enough to check against one of the two chunks. So if an overflow happens, then the result will be smaller than both chunks. Yeah. And if this happens, then it means that we need to carry over a 1 to the next chunk. And now the question is how we implement this. So one option would be to just now write to the next chunk, but then this complicates things in as far as that you need to track if the next chunk even exists, because if it would be at the highest allowed I, then the next so that then the I plus 1 would no longer be valid. So the best approach is to create a chunk for the carryover values outside the loop after the result. After the begin to result, we just create a t chunk carry. T chunk. And we initialize it with 0, obviously. And then if this overflow happens, we just can write carry plus plus inside the code block here. And now we of course need to apply this carry somehow. So and the thing is, we might have a carry over, and then we add the two chunks, and if the two chunks add the two chunks can add such that we would generate yet another carry over to the next to the over next block. So worst case, we might generate two carryovers. So this needs to be somehow smartly handled. And one approach would be, for example, to add to modify one of the two chunk values. Let's say we will modify chunk 1. So the approach is you basically copy this code that you already wrote, just that you will, instead of result p data I, you will have just chunk 1 is you will need like a helper chunk 1. You would need a temporary variable. So make one in line 210. Call it chunk t for temp or something like this. Although, wait, can we do it? No, we can even do it with only... No, we cannot. That should be fine. Chunk temp, which is equals chunk 1. Then we will add to the chunk, to the new chunk, so that chunk temp will get modified, will be plus equals carry. So if there is a carry, then it adds it. And then we set carry to 0 because we have used it. And then next line. And then we test if temp chunk is less than chunk 1. Which would indicate that a carryover happened. Then carry plus plus again, meaning we need to carry over to the next. And in the code below, you will just replace chunk 1 with temp chunk. Okay. Right, so we can have, in the worst case, 2 carryovers. If we had one, a plus, another one is generated inside the current chunk. And the last carryover, which remains, is just dropped because we had too many values, at too high value, I mean, for the length of our number to represent it. There would be another approach where we would then grow the size of our big int by one chunk so that we can accommodate the carryover. But I don't think we would want to do this, since normally when you are working with integers, you want them to be fixed size. So already here our approach that we allow them to be different size and then just take the size of the bigger one is already a very convenient deviation from the standard. So I think this is good enough. We just need to test it whether it's working. So it will need a test case to be set up in the main function. And I think given the remaining time, we will just do the addition, and the subtraction will be then for the next lecture. So you can already start thinking who would like to do it and how. It's not that much different to the subtraction case, so it's reasonably easy to do. Sure. I guess it would be also helpful to put the numbers into a calculator and then write a third one, which would be the result of the sum operation, so that we have something to compare with. In fact, you can just, may I? I will take the mouse for a second. Since this number is only 64-bit, C++ can do it for us. If it would be a bigger number, then it couldn't. Also, then we couldn't write it in this notation. We would need to put it as string and then use from hex, which was a homework, but we haven't used it here, so we won't be using it for now. Yeah. But for testing, that's why we chose a rather small chunk size here in this lecture, so that we can easily just use the C++'s own 64-bit handling to generate test data. That's really convenient. If we would want to make this work as a production build, we would of course set the chunk size to be 64-bit, so then it wouldn't work for testing this nicely. But in fact, when I have the mouse for a second, there is a preprocessor definition, hash def hash so if this is a debug build, then this code block is enabled. If it's a release build, then the other block. So this way, you could have a short value to test your mechanisms and run your test in a debug build, while in a release build, you would take the largest one you can that makes it as efficient as you can. And you could even improve that hash if what was it, mx64, I think, or rather maybe if in64 is this defined by default, hash and if no, we don't have this defined. There are preprocessor definitions which tell you which architecture you are on. So in principle, or you can just set them manually. We could add here somewhere. Could add like a Win64 for the 64-bit and not for the other one, so that we can tell those configurations apart. And here we could then even choose whether we use a long or in64 in the release build, depending whether we are building for 32 or 64-bit. But since the compiler, even on 32-bit, can do 64, it just implements it manually with multiple operations. Kind of what we have done here ourselves, just a bit simpler, because it just has two chunks and not more, and it can use directly assembly instructions. Yeah, but that was just a small detour. We still need a test case, and ideally you would think about the test data a bit more, so to generate ones which have a carryover over more than one chunk and so on. But I think here for now let's just add one test case and then see whether it just in one simple case does what we want it to do. Yes, correct. Mm-hmm. Mm-hmm. The leading zeros can go away. Only the zeros on the back should remain because when you write it, yeah. Correct. You would alter it. Oh, I know what you mean. Wait. With a sample. You mean here if you would have which one is the first? That's the low. That's the high. So you mean if you would have here zeros? Um, however many zeros that would be, you don't need them because this will be treated as a 64-bit number and it will pad them into the low word automatically either way. It will not just bunch them together. So when you're using hex notation, uh, for the compiler, so not inside the string but really like this, you can always drop the leading zeros. It will always give you the right value. Yes. You can just write number 1 plus number 2. We have an operator defined, so well, that's the point. You want to compare whether it will be the same as number 3. Yes, because in line 153 we just allow the compiler to add two 64-bit numbers and use this as input, while in line 155 we're actually using our own implementation to do the addition. Well, we would like, if it's false, then return false, else return true, because we might want to have more than one test case. We would prefer the if to be if not equal, then return false. Because then we can add more test cases and will not just say everything's fine after the first one was fine. Because the first one is fine, the second might still fail. So only if all the test cases are fine at the end, we return true. No, the other test cases would be with other input data. We would handcraft input data which triggers carry over one chunk, over two chunks, and see if this always yields the correct result. Um, but since we are running out of time, we could skip that. We will in the next lecture we'll do the subtraction, and then we can also take a look into manually handcrafting some more test cases for our addition. Here let's just add a return true in line 163, so that we can compile the project, and let's run it. Oh, and we should of course write some text like test complete, test failed, etc., so that we know when we look in the console what happened. Okay, let's run. Yeah, let's use it first. It doesn't like something. Oh, did we forget to return value? Wait. This is a mistake. This should just be the definitions. too much copy and paste. Okay. Not okay. It crashed. Why? It crashed at I0. Wait, result. Oh, we did not initialize result. We missed to copy a line. Log data. This line escaped. Some. No, did not. Let's put a breakpoint and run it again. Result. But it fails for some reason. Is size not correct? C8, no, the size is right. Weird. We didn't add test cases for the bytewise operations because we were running out of time. So apparently that was a mistake. Okay, so 8 is correct. Size is greater 0. PTR. Oh, haha. Alloc data just allocs the data, but we still need to assign it. So this mistake will be replicated a couple of times. Okay. Yeah, that's why test cases are important. Okay, and let's see what it said. Test success, perfect. Nice. Okay, so let's see what we can improve. Test add. Test failed. We could add more text, but since like what would be the expected value and so on. And we have a few more minutes, so we can handcraft a few more test cases. So let's call the test case 1b. Actually, we could maybe even make it more convenient. Nah, it doesn't matter. 1a is equal 0x0, test 2b, sorry, to a. Right, I wanted b. So we just take the values here. The copy it somehow didn't take. So that we don't need to copy them by hand, we don't just need them to write them here. 1, 2, 3, 4, 5, 6, 7, 8. Okay, then repeat it and let's see. So our chunk size is short, so it's always 4 nibbles. Yep, it's a short. So it's always 4 nibbles. So if we would have something that causes a carryover like well, 1, 2, 3, 4 and 1, that should cause a carryover. Then let's see if this works correctly. The result we know we should get is oops. I think this we should get. So sum b well, sum we can override the old one. We'll just say sum b. Or actually, we could also do it in a one-liner like this. Yeah, this is better. So test 1 failed, or test A failed. Test failed A, test failed B. Let's see if this will be correct. Okay, the carryover worked. But since we don't have the sum, we can look here what we got internally. Okay, can't I copy the address? Copy value, I can 0, 0, 0 and the 1. So it works. So now let's create a test case with 2 carryovers. So here we just FF and here okay, and this gets then already a bit complicated to calculate in one's head. I guess it will be something like sorry 1 2 3 4 1 2 3 4 theoretically, so this should probably be a 2 and then we'll have here probably something like this, but let's check it. Hex plus no, it's not quite right. We got such a result. And this of course then needs to be called then test C. C C. Okay, let's put a breakpoint and then let's run it. Yeah, it's still working. That makes me think if we cannot somehow simplify the code that we have written. Let's remove those breakpoints. We have 2 minutes left because we make this a little bit complicated. And the carryover, yeah, you can disconnect. And the carryover is always a 1. Hash if 0 hash else hash and if chunk 1 so we have here our data, we have here a carryover, but we want the carryover to first be integrated into this. Well, we still need a temp value. That is not, we don't save much. New chunk is this, new chunk is that, and then once we're done we set this then here we make this is equals new chunk plus carryover, and carryover is equals 0 and carryover always is, in this case is 1. We don't have more than 1 carryover. This should also work, but it still needs a temporary value. It still behaves correctly as we see. I don't think we can completely get rid of the temporary value because if this case happens, it's already carryover for the next iteration. Yeah, that's maybe a bit more elegant, but it's not really reasonably shorter. Right, and since we only then have a carryover to the next block, where will this always work? New chunk and carry. Now this has a catch-22. If we do it like this, if this would be like just one less of a, like this would be just all F's, then this would also cause a carryover. So we actually would here also need to do this test. And it will not be more efficient, it will be just differently structured. So let's just leave it at how we have made it here. This is I think just as efficient as the other one. Good. So we are running out of time, so I will upload the things to Moodle. the homework you see here. The homework here will be scheduled not for 2 lectures from now, but for 3 lectures from now, since it's a bit more complicated and we have not even finished the subtract implementation, what we'll do the next lecture. So for this one you will have more time. It's also a bit bigger and a bit more complicated. Yeah, that's it. So we will see each other for the lecture in 3.5 hours, or if you are not participating in the lecture, we'll see each other next week. So see you. Bye bye.